Section 1.2 is properties of real numbers. I can graph and order real numbers, and I can identify properties of real numbers. Big ideas. The set of real numbers has several special subsets related in particular ways. Algebra involves operations on and relations among numbers, including real and imaginary numbers. The properties of real numbers are relationships that are true for all real numbers. So real numbers are formed by the set of all rational and irrational number. Every number that you know right now is a real number. And every real number can be graphed as a point on a number line. There's a diagram on the top of page 12 that shows the relationship between sets of real numbers. So natural numbers are the numbers that we use to count. That naturally, when we were little, we started counting 3 puppies, 4 books, things like that. Okay, 1, 2, 3, 4. Whole numbers are the natural numbers, and we add in 0. Think about 0 like it's a whole. Okay, we add that to the natural numbers. Integers are plus or minus the natural numbers and 0. So it's all of our natural numbers and their opposites, and then 0 obviously as the whole number. So -2, -1, 0, 1, 2, and it continues in both directions, but it doesn't include any decimals or fractions. Okay, rational numbers, however, are integers and any numbers that can be written as a fraction, terminating decimal, or repeating decimal. Okay, so if they have a decimal or a fraction, but that decimal terminates or repeats, then it's a rational number. And keep in mind that natural numbers are also whole numbers, are also integers, are also rational numbers. Whole numbers are also integers, are also rational numbers. Integers are also rational numbers. Now we get to irrational numbers, and these numbers cannot be written as an integer or fraction and have decimals that do not terminate or repeat. These are things like the square root of 7, pi, things like that. So square root of non-perfect squares are irrational. They don't terminate or repeat when you type them in your calculator. Your window shows what it can, but it actually continues on. Same with pi. And then again, together the rational numbers and irrational numbers make up all real numbers. We can classify a variable by giving the most specific category in which it belongs. So here, our school is sponsoring a charity race. Which set of numbers does not contain the number of people, P, who participate in the race? So if we're talking about the number of people, that could be a natural number. We can count that. It could be an integer. Remember, natural numbers are also integers. We're not going to have like -7 people who participate, but 7, for example, is an integer, a natural number and an integer. Natural numbers and integers are rational numbers, which means an irrational number of people, we're not going to have an irrational number of people who participate. We're not going to have square root of 10 people or anything like that. So the one that does not contain is irrational. Now, if each participant made a donation D of $15.50 to a local charity, which subset of real numbers best describes the amount of money raised? So if we have $15.50, okay, and we don't know how many donations there are. So $15.50, if we look at that, that's not something we're necessarily going to count when we start at 1, like 1, 2, 3, 4. Okay, it's not a natural number. It's not 0, so it's not a whole number. It's not an integer because we have that decimal. So as soon as we see a decimal, we know it's either going to be rational or irrational. But that's it. It doesn't go any further down with rational. And since 1550 ends, it terminates, this is going to be rational. Okay, so first thing we want to do is figure out, is it rational or irrational? If it's rational, try and break it down further if it can be. If it's a negative number, it could be an integer. If it's 0, it's a whole number. If it's 5, it's a natural number, things like that. Now, would the answer change if we were referring to the amount of money in pennies rather than in dollars? So if instead of $15.50, we were talking 1,550 pennies or cents. Okay, yeah, our answer would change. Here would be a natural number. Okay, we know it terminates, so we know that it's rational. If we break it down further, it's positive. Positive doesn't have a decimal. It is natural, a natural number. In example 2, we're going to graph numbers on a number line. The purpose of this, guys, is when we only have two things, we can compare them fairly easily with like less than, greater than, less than or equal to, or greater than or equal to. But anytime we have more than two, to put them in order, a number line is helpful. So first thing I'm going to do is to start off, and there's only 3 here, we could have maybe figured this out anyway, but I'm going to start off by writing them in decimal form. And again, the more numbers we have, the more items here, the more beneficial the number line is. So -5/2, I'm going to switch to a decimal, -2.5. Square root of 2, I know square root of 2 is going to be between 1 and 2 because it's in between perfect squares 1 and 4. But in my calculator, I get approximately 1.41. And 2.6 repeating is already in decimal form. So at about -2.5, between -2 and -3, I'm going to put a point, and I'm going to label it what they gave me originally. Square root of 2 is about 1.41, so in between 1 and 2, a little bit closer to 1. And again, I'm going to label it what they gave me originally. I want that exact answer, not the approximation. And then 2.6 repeating is 2 2/3, so 2/3 away towards 3. And they don't have to be perfect here, guys, but it should be closer to what we need. So this one's a little bit closer to 3, this one's a little bit closer to 1. That's pretty close to right in the middle, to give us a pretty good approximation there. Now feel free to pause here and give this one a try if you'd like. Square root of 3 is approximately 1.73. Again, we know it's in between 1 and 2 because 3 is in between perfect squares 1 and 4. A little bit closer to 4, so we know that our square root is going to be a little bit closer to 2. 1.4 repeating is already in decimal form, and 1/3 is 0.3 repeating. Take 1 divided by 3. So square root of 3 is in between 1 and 2, closer to 2. -1.4 is between -1 and -2. 1.4 repeating, so this would be like 1 4/9. And 1/3 is in between 0 and 1, a third of the way. Okay, so we've graphed numbers before on the number line. The only thing here is we're going to have irrational numbers, we're going to have integers, we're going to have all different types of numbers, real numbers there, and we're just going to put them all in the same number line. Again, here, a number line is helpful if we have a lot of numbers, but when there's only 2, we can use inequality symbols. So here we're going to order these real numbers. If we look, the square root of 17, we can approximate. 17 is in between 2 perfect squares, in between 16 and 25. Okay, 17 is close to 16, which means our answer is going to be close to 4, because the square root of 16 is 4. So the square root of 17 is going to be about 4, but we know it's going to be a little bit higher because it's more than 16. So it's going to be a little bit more than 4. And here we have 3.8. So here we have 4-ish. Here we have 3.8. 4 is greater than. So the square root of 17 is greater than 3.8. And again, we've done this before in algebra. Otherwise, we can type it in our calculator. When we do that and take the square root of 17, we get 4.12. So like we said, a little bit more than 4, and that's greater than 3.8 as well. Now feel free to pause here and give this a try if you'd like. So 26 is in between 2 perfect squares, 25 and 36. 26 is really close to 25. So we know this is going to be close to the square root of 25 is 5. It's just going to be a little bit more. So if I'm comparing 5 point something to 6.25, I know that 5 is going to be less than 6. It doesn't matter what my decimal is here. I know that it's not 6 because it's not quite to 36, and the square root of 36 is how I get to 6. So I know this is going to be less than. So the square root of 26 is less than 6.25. The other thing I can do here, guys, is I can actually take the square root of 26. And when I do that, I get 5.10. And when I compare that, it's still less than. So I'm right. Now, if A is less than B and B is less than C, what is the relationship between A and C? First thing you want to do is figure out, do we have enough information? And yeah, we do. If A is smaller than B and B is smaller than C, then A has to be smaller than C. A is less than C. If you're not sure, pick some numbers and plug them in. Let's make A 2, B 6, and since we made B 6 there, here we can pick 6, C 10. It doesn't matter what numbers we use, guys, as long as we keep our B's the same and we make them true statements. 2 has to be less than 6 and 6 has to be less than 10. Now we can check the relationship between A and C. And 2 is less than 10. So A is less than C. The opposite or additive inverse of any number A is negative A. The opposite of a number, the sum of a number and its opposite is 0. And that's our additive inverse property. We take a number, add its opposite, and get to 0. The reciprocal or multiplicative inverse of any non-zero number A is 1 over A. The product of a number and its reciprocal is 1, always, and that's our multiplicative inverse property. If you look at the take note on page 14, they have a few more properties there. We've talked about commutative and associative properties. Identity properties are what get us back to the identical thing. So we can take a number, add 0, and get back to A, which is identical to where we started, or we can take a number, multiply by 1, and get back to where we started. And then we've talked about the distributive property as well before. Commutative moves them. Okay, A and B swap places. Associative property deals with our grouping, so our grouping changes. And with the distributive property, it takes multiplication and switches it to addition if it's addition on the inside. So it kind of combines both properties. The A on the outside gets multiplied to everything on the inside. Which properties does the equation illustrate here? If we look, it equals 1, and we're multiplying. So anytime we can get to 1, it's going to be our inverse property. Okay, we multiplied something times its reciprocal, so this is the multiplicative. The inverse property. Or you could say the inverse property of multiplication. In B, the thing that changed here is our order. If we look, our group is still the same. It's still a 3 and a 4 and a 4 and a 3, but what changed is our order. It moved, and so it's the commutative property. Of multiplication. Again, if things move around, it's the commutative property. If they change their grouping, which that one didn't, it's the associative. If we look here, guys, the only thing that changed, our order didn't necessarily change. We have G, then H, then 2G. But what changed are the pieces themselves. So 3 moved from outside to inside with both things. This is the distributive property. Take some time to get comfortable with those properties on page 14. Those are going to be really helpful moving forward. Quick recap for this section. The set of real numbers has several special subsets related in particular ways. Algebra involves operations on and relations among numbers, including real and imaginary numbers. And the properties of real numbers are relationships that are true for all real numbers. And that's all I have for section 1.2.